Welcome back to this course of X-ray crystallography. In the previous couple of lectures, we have learnt about the structure factor and scattering factor. So, we would like to continue in this direction in next few lectures, and we will try to understand the importance of structure factor and how one can relate structure factor to electron density through a Fourier transformation. And then also we will try to understand the origin of systematic absence using these structure factor equations. So, the theory of structure factor, as we are continuing theory of structure factors, which we write as FHKL, and as we have already understood that FHKL is nothing but the ratio of the amplitude of scattered X-ray beam from all the atoms in the unit cell divided by the amplitude of scattered X-ray beam from a single electron. So, this atomic scattering factor, this structure factor capital F HKL, it is a function of HKL. That means for different plane HKL, the value of this F HKL will be different because the plane that we are talking about have different orientations. So, different atoms present in the unit cell will have different contribution to the diffraction factor, that is the FHKL, on that particular plane. So, the structure factor for this plane will be different from that plane, and it will be different from this plane, it will be different from that plane. All possible planes will have different scattering factors. So, it is a function of that HKL, that is the Miller indices of the planes, and position or location of the atoms, because these atoms are actually the scattering centers, which are scattering centers. So, what we need is that we need to develop an expression between FHKL and rho xyz, where rho xyz is the electron density associated with the atom location xyz, and there may be n number of atoms located at n different sites in the unit cell. So, we need a nice equation to equate these two quantities FHKL and rho xyz. So, to understand this, what one needs to do is to go through a process where we assume we are having a simple harmonic motion, and from there we would extend our understanding. Suppose we have a point A moving in a circular path. So that point A moves in a circular path with a center at O, and this point A has a fixed angular velocity equal to omega. So at any given point of time, the projection of OA on, say, this is the x-axis, is OB, and OA represents the vector F, and projection of OA on x-axis is at B. So at a given position of A making an angle phi with the x-axis, and this being rotated along the circumference of the circle at a given fixed angular velocity omega, this represents a simple harmonic motion. So if I try to plot the linear displacement of B with respect to the origin O, this motion would look like a curve like this. So this is the plot of linear displacement of B as a function of F and phi. So at this direction is your direction of phi, and we start it here at 0. This is the direction of phi, and the maxima is reached when phi equal to pi, and that is equal to F cos phi equal to F at pi equal to phi. If the angular velocity omega is constant, and then phi is proportional to omega t. So this will represent the linear displacement of B along the direction of phi. So now suppose if there is a phase difference, we draw the same curve with a phase difference of delta with respect to the origin, So in that case, these terms f and delta also characterizes a vector of length f in a complex plane making an angle delta with the positive real axis x. So the situation is like this. So in that, this is the drawing of f in a complex plane where f makes an angle delta with the x-axis. So one can write f equal to a plus ib, which is nothing but cos delta plus I sin delta. So this x representation a plus ib is termed as the rectangular form, and cos delta plus I sin delta is termed as the polar or trigonometric form. So from here one can write the value of mod f equal to it's a small f, value of f equal to a square plus b square and delta equal to tan inverse b by a. This is how one can represent a simple harmonic motion of a particle in a circular path with a vector f. Suppose we have a crystal here and X-ray beam is impinging on the crystal and it diffracts in all possible directions. So, when such things happen, multiple waves are scattered at various directions. So, then we need to understand how these waves are superposing. So, we need to understand little bit of superposition of waves. So let us assume three scattered waves F1, F2 and F3 with phase angles delta 1, delta 2 and delta 3 are scattered. They are scattered simultaneously. So, in a vector space diagram, we can represent these three waves in this way. Suppose this is F1, this is F2, and F3 is in a different direction like this. So, the overall wave, the summation is capital F. This F1 is making delta 1 here, F2 is making delta 2 there, and F3 is making a phase angle of delta 3 here. So, now if we use the component projection method to do this addition, then the corresponding x component turns out to be F1 cos delta 1 plus F2 cos delta 2 plus F3 cos delta 3, which can be written using a summation over I Fi cos delta I. Similarly, y can be represented as sum over I Fi sin delta I. Whereas f equal to x plus iy. So, modulus of f is nothing but square root of x square plus y square, which is now equal to sum over I Fi cos delta I square plus sum over I Fi sin delta I whole square, and then a square root of this. And the overall angle of f, that is the phase angle of f, which is alpha, can be written as tan inverse y by x, which is equal to tan inverse sum over I Fi sin delta I by sum over I Fi cos delta I. So, this is how the superposition of waves can be calculated, and we learned the same in the previous class as well. So, what does a structure factor represent? FHKL, the structure factor, is the resultant of n waves scattered in the direction of the concerned reflection, that is perpendicular to the plane HKL, by the small n atoms present in the unit cell. All these waves have an amplitude proportional to the atomic scattering factors, which is represented as Fi, and a phase angle delta I with HKL as well. So what we need? We need an expression for the overall phase delta with x, y, z and hk and l. So what we know is that the plane HKL cuts A in H parts, B in K parts and C in L parts. So when we have a set of HKL planes with a distance dHKL and a set of reflections, a set of wavelength, X-ray wavelength, when a diffraction occurs from these two planes HK of in this case HKL, the phase difference for one cycle is equal to 2 pi. So the phase difference for unit translation along x, y and z direction would be equal to 2 pi h, 2 pi k and 2 pi L for corresponding the phase difference about one cycle. So, the phase difference between 2 points 0, 0, 0 and x, y, z is nothing but delta, which is equal to 2 pi hx plus ky plus lz. This is the expression of phase difference between the sets of reflections from a set of parallel planes with indices h, k and l. So, one can calculate the mod of FHKL as sum over Fi cos 2 pi Hxi plus Kyi plus Lzi whole square plus sum over Fi sin 2 pi Hxi plus Kyi plus Lzi square overall square root. So, we write this term as A and the sine term as B. So, one can write FHKL is equal to A square plus B square square root of that. So, one can write FHKL equal to A plus IB and alpha HKL is equal to tan inverse B by A. So, now let us see a situation for two different values of HKL which are related by a center of inversion. That means I am talking about HKL and H bar, K bar, L bar. Let us first see it pictorially. Suppose this vector represents FHKL and this vector represents F H bar, K bar, L bar. If we join the two tips, this portion represents VHKL and this portion represents B H bar, K bar, L bar, and here it is A H K L equal to A H bar, K bar, L bar. The phase angle for the HKL reflection is alpha HKL. Phase angle for the F H bar, K bar, L bar is alpha H bar, K bar, L bar. So, now from the figure we can easily see that A HKL is equal to A H bar, K bar, L bar. BHKL is equal to minus of B H bar K bar L bar. It's of opposite sign. And now as I is proportional to f mod of f square, we can write IHKL equal to AHKL square plus BHKL square, which is equal to AHK H bar K bar L bar square, because AHKL equal to AH bar K bar L bar and BHKL equal to minus of BH bar K bar L bar square, which is equal to AH bar K bar L bar square plus BH bar K bar L bar square, which is equivalent to I H bar K bar L bar. So that means we arrived at a situation where IHKL is actually equal to IH bar K bar L bar. What is this expression called? We have already discussed about this. This expression, this relationship is called the Friedels law. See, although this IHKL is equal to IH bar K bar L bar, which actually means mod of F HKL square is equal to mod of F H bar K bar L bar square, but not F HKL equal to F H bar K bar L bar. So what we should actually write is, but H bar K F HKL is not equal to F H bar K bar L bar, because they have the angle different, which means the alpha HKL is equal to minus of alpha H bar K bar L bar. So today we have seen in this lecture how one can derive the expression for structure factor once again using vector space diagram and involving the complex numbers, and from there how to show that the Friedels law can be arrived at using these structure factor expressions. So we will continue in the next class with the structure factor having a relationship with electron density.